about. So I just remind you where we are in my lectures. I did the climate feedbacks last time. I'll talk about the faint young sun problem today. And actually that will be, I can go through it quicker than usual because a lot of what I usually do in that is on the carbonate silicate cycle, and we've already done that last night. The next lecture is on the rise of oxygen and ozone, and it's actually questionable as to what order these lectures ought to be done in, because you actually need to understand something about the rise of oxygen in order to appreciate the solutions to the faint young sun problem. But I'll try to address that. We'll do the faint young sun problem first, and I'll refer to the lecture that I guess I will give tomorrow morning on oxygen as we go through this. All right, so let's do the faint young sun problem. I mentioned it last night. I'll talk about long-term climate to begin with, just giving you an outline of what the Earth's climate history has been like. Talk a little bit about solar luminosity changes, which most of you are familiar with. A little bit about constraints on atmospheric CO2 from geochemical evidence, but I won't belabor that. And then I'll talk about the methane greenhouse, which is actually my favorite part of this talk these days. Let me just show you two pictures on the geologic time scale. This is something that geologists learn in undergraduate courses, and I was not a geology major undergraduate, so I got interested in this in graduate school, and I actually made a Xerox copy of a geologic time scale and taped it on the wall in front of my desk, because you have to learn all the periods in order to read the geologic literature. So you probably can't read all the periods here, but this is part of the geologic time going back to the beginning of the Cambrian era. We talked a little bit about the Cambrian explosion of fossil life yesterday. That begins around 542 million years ago now, where the first shelly fossils come in. What I want to focus on here is not all the biological evolution that has gone by in this time, but just the climate. And I've marked the major ice ages on this slide. So and let me define an ice age. When we talk about ice ages, usually you think the coming and going of the glaciers. And the last ice age was when Switzerland and Europe were all covered in glacial ice. Well, that's the short-term definition of an ice age. But the long-term definition, and we're in an interglacial period amidst a series of glacial periods if you use that definition. The long-term definition, which is the one that's relevant to Earth evolution, is that you're in an ice age if there's ice at the poles. And so we're in the ice age right now because there's ice on Greenland and Antarctica. We've been in an ice age for about the last 35 million years, because that's when we think that Antarctica started to become glaciated. If you go back to, and this is what we call the late Cenozoic ice age, because we're in the Cenozoic era right now. If you go back before the Cenozoic, you get into the Mesozoic era here. That's when the dinosaurs were roaming the Earth, and you probably already knew that the Earth was warm at that time. There were dinosaurs running up on the north slope of Alaska. And that Alaska was sitting right where it is right now. There were crocodiles living in Siberia. So there was little or no polar ice at that time. The Mesozoic was very warm. You go back before that, there was a long ice age, about 80 million years, which we call the Permo-Carboniferous ice age, which was more or less like the ice age that we're in right now. There was ice on the poles. And then it was warm before that. There's what we refer to as a greenhouse icehouse cycle that actually may have to do with plate tectonics and the formation and breakup of supercontinents. It's called the Wilson cycle. So the Earth gets hot and cold, and it's probably CO2 going up and down during the Phanerozoic that's doing a lot of this. There's a very brief ice age at the end of the Ordovician, which is curious because it's could be less than 500,000 years to a few million years. It's much shorter than the other ones. And then the Cambrian was warm. Now, if we expand the geologic time scale, this is the geologic time scale going back to the formation of the Earth at 4.6 billion years ago. So now the Phanerozoic is compressed up at the top, and you see the rest of geologic time, which used to just be called the Precambrian because it was prior to the Cambrian, but now we divide it into the Proterozoic and Archean and Hadean eras. Again, let's look at the ice ages here. These two arrows right here are the two best studied snowball Earth ice ages that I talked about last time. These are the ones that Paul Hoffman and Joe Kirschvink have studied at about 600 and 700 million years ago. Then it was warm during the Proterozoic. There's no evidence of ice for about 1.5 billion years. So that's a curious thing. There's an ice age right here at about 2.4 billion years. That's right when oxygen goes up for the first time. And that's, I'm going to come back to that. I don't believe in coincidences, and so just to give you the punchline before we get there, if there was a methane greenhouse back in the Archean before the rise of oxygen, then when oxygen goes up, you expect the climate to get cold, and so you would predict that you might get a glaciation. So I think that that's probably what goes on here. This one also has evidence for low latitude glaciation, and so this one may be a snowball like the late Proterozoic glaciations. And then finally, there's an ice age right here at about 2.9 billion years. I used to have a question mark on the diagram here because it hasn't been as well studied, but there's now known glacial deposits on 3 continents, I believe. And this is important too because there are data that I won't talk about from oxygen isotopes that suggest that the Earth was very warm back in its past. And you know, there's Paul Knauth at Arizona State has argued for several decades that the Archean Earth was, the mean temperature was 70 degrees Celsius, which is not impossible, although I consider it unlikely. And I used to entertain that notion until I learned about this ice age at 2.9 billion years. It's really hard to have the Earth be 70 degrees Celsius and then go into an ice age and then pop out of that again. And so it makes it look as though the early Earth was warm most of the time, but not greatly warm because it could go into ice ages. So the bottom line of that is that ice only covers the poles about 10% of the time during the Earth's history. The other 90% of the time, the Earth is warmer than today, and that's something to bear in mind. Of course, as I mentioned in my first 2 lectures, we could get back to that point if we burn enough fossil fuel. So if you're an optimist, you say we're just getting back to where the Earth likes to be, right? But maybe not humans. All right, well, why is this all interesting to a physicist? It's because we also have good reasons to think that the sun was less bright back in the past. So it's curious that the early Earth was warm. This is a solar luminosity curve from a very old solar evolution model by Douglas Goff that was published in 1981. It's well known to astronomers and astrophysicists why main sequence stars get brighter. They're fusing hydrogen to helium in their cores. The cores become denser, they contract, they heat up, and that makes the fusion reactions go faster. And the interesting thing to me is that the standard solar evolution model hasn't really changed, to my knowledge, much in the last 30 years. So this 30-year-old curve is still pretty good. I still use this one because Goff was kind enough to put a little analytic formula in his paper that you don't need a big computer model to figure out. You just put in your little equation there and you get solar luminosity at any time in the Earth's history. I would be glad if any of you do these calculations and have a better calculation than Goff if you would put it in parametric form like that, because it's really useful to climate scientists. All right, now there's about every 5 or 10 years, some astrophysicists will suggest that the young sun wasn't really faint. There are ways to get astronomical solutions to the faint young sun problem, which I didn't really phrase, right? The sun was less bright, but the Earth was warm, and so that's the faint young sun problem. If the young sun was more massive than today, then it could have been brighter than is predicted by the standard model. And then you would just need to have a very strong stellar wind, about 10 to the 4th times more intense than the present day solar wind, in order to remove the excess mass. I have some slides on that, but I've put them in backup here because I'm not going to go through it unless people really want me to. The latest word that I know, I'm familiar with on this is Brian Wood and colleagues at University of Colorado have placed some constraints on this by looking at nearby solar analog stars, young stars. And they look at the at neutral hydrogen that builds up in the astrosphere. It's analogous to the heliosphere. The solar wind runs into the interstellar medium and you build up neutral hydrogen at the boundary there in the bow shock. This happens around young stars, and you can't observe stellar winds directly because they're fully ionized, but if you build up the neutral hydrogen there, you can see that in Lyman alpha. And so Wood and colleagues have looked at young stars, and their conclusion, which I do have slides if you're interested in that, is that there may be a lot of mass loss, but it occurs very early, within the first 100 or 200 million years of the star's formation. A lot of mass loss means maybe up to 1% of the mass of the star, which would give you something like a 30% increase in brightness. That would solve the faint young sun problem, but it only does so for on the order of 100 million years, and the geologic time is just beginning to get going by that time, so it doesn't really address the problems of the Earth's climate evolution. All right, so I'm going to assume then that the standard solar model is correct for the rest of this talk, and then I'm going to follow Carl Sagan again, because he and George Mullen were the first ones to point out that what we now call the faint young sun problem. The theory of stellar evolution had been invented in the 1950s or so the astrophysicists were all familiar with this, but Sagan and Mullen were the first planetary scientists to consider the effects of main sequence solar evolution on climates of Earth and Mars. So they did some calculations with the climate model. These calculations shown here are with my own climate model, this one-dimensional radiative convective climate model that I described in my first lecture. Here's a graph that starts from 4.5 billion years ago up to present, and the yellow curve is Gough's solar luminosity curve there, which goes with the scale over here on the right. The bottom dash curve is the effective radiating temperature of the Earth calculated with this 1D model. And this calculation is done the same way that Sagan and Mullen did. Let's just assume for the sake of argument that the Earth's atmosphere hasn't changed. It has the present day CO2 amount and a variable water vapor amount, which I'll talk about in a moment. Then the greenhouse effect is represented by the white area on the diagram. And T sub S is the mean global surface temperature. That's the effective radiating temperature plus the greenhouse effect. So if you do this simple calculation, then you find out if you go back in time, the mean global temperature drops below the freezing point of water about 2 billion years ago, which was right when Sagan and Mullen had it happening in their model. And then that would be enough to kick the Earth into snowball Earth if that were to happen. And as we talked about last time, we know ways to get out of that, but actually it doesn't look like the Earth was that cold. Most of the time there wasn't glaciation. And so that is really another, that's the way to define this faint young sun problem. Well, water vapor is in there. Remember, I said feedbacks are important in these models, and so water vapor, the assumption in the climate model is that you have a fixed relative humidity profile. And so if you fix the relative humidity is the percent of saturation, and so that's then tracking the saturation vapor pressure curve of water. So when the climate is colder, you have less water vapor. When the climate is warmer, you have more. And so today, the greenhouse effect from CO2 and water vapor is about 33 degrees. And as you go backwards in time, under these assumptions, the climate gets colder, you get less water vapor. That's that positive feedback loop. And so the positive feedback loop makes the problem worse because the surface temperature is declining faster than the effective radiating temperature as you go backwards in time. All right. Okay, well, how do you solve the faint young sun problem? There's lots of solutions to it. The ones that I'll focus on all involve greenhouse gases, and we've talked about greenhouse gases. They absorb and re-emit the outgoing infrared radiation. The ones that are important on Earth today are mainly CO2, water, and methane. Water, though, is giving us this positive feedback, and so that's exacerbating the problem rather than solving it. So you want to focus on CO2 and methane are the ones that I'll focus on today. Although I'll bring up ammonia, too, because Sagan and Mullen liked ammonia. Let's start with CO2, and this is the part that I can do very quickly today because I went through this whole cycle last night. You've got the carbonate-silicate cycle that is controlling CO2 on long time scales. And so if we talked about snowball Earth. If you freeze over the oceans, then the silicate weathering shuts down, volcanic CO2 builds up in the atmosphere, and you get out of snowball Earth. But you don't have to get into snowball Earth in order for this negative feedback to work. As the climate gets cooler, then volcanic CO2 should build up, and because silicate weathering slows down. And so the argument then is that in order to maintain, most of the time you don't have anything extreme that kicks you into a snowball glaciation. This cycle is working more or less as it does today, and that keeps the climate warm enough that you always have liquid water. The curious thing is that sometimes it doesn't work and you get into these snowball Earth episodes. That's a different story. So if you buy that story about the carbonate-silicate cycle, then you can say, all right, well, suppose it's just high CO2 was the answer to the faint young sun problem. How much CO2 do you need to counteract a 30% increase in solar luminosity? Well, if solar luminosity is increasing with time like this, then CO2 has to be decreasing with time. And that's a calculation you can do with your climate model. So these are some calculations that I did back actually in '87 and republished in this review paper in Science in 1993. This is the CO2 this time from 4.5 billion years ago up to the present in giga-annum, billions of years before present. The CO2 partial pressure in bars, remember we're at about 3 times 10 to the minus 4 bars today, right down here. And then over on the right-hand scale, that's the CO2 concentrations in PAL. PAL means times the present atmospheric level. And that's a term that I'll use frequently in the next couple of lectures. So here we are at 1 PAL today. If you go back to the beginning of the Earth, the sun was about 30% less bright, according to the standard model. Then you need a minimum of about 1/10 of a bar of CO2, which is about 300 PAL of CO2, just to maintain temperatures above freezing. And in fact, this gray area represents the range of climatically acceptable CO2 levels. And what I've assumed here, I should say that the way this is drawn is these, what look like error bars, these are the 2 Precambrian glaciations. Actually, I didn't know about the Mid-Archean glaciation at this time. But this is the glaciation at 2.4 billion years, and these are the snowball Earths in the late Precambrian. And when you're in a glaciation, the temperature can't be too low. It may go very low during snowball Earth, but then it rebounds. And so most of the time you're not below about 5 degrees Celsius. That's about what the Earth was during last glacial maximum. And you also can't be much above 20 degrees Celsius. Remember, we're at 15 Celsius today for a global average. If you get up above 20 degrees Celsius, then you get back to the point where we think Antarctica was no longer glaciated. So that's probably an upper limit for glaciation. So you have both, during these glacial periods, you have both upper and lower limits. And during the other periods you don't, and so these are curves that are drawn in there to just sort of connect the dots there. And this story then, could work. There's no reason conceptually that you couldn't just solve the faint young sun problem with CO2. And in fact, when I used to give this talk a long time ago, it would just quit there because I was happy with that solution. Now, in the last 15 years or so, the geochemists have gotten into the argument, and they've tried to use geochemical indicators to place constraints on atmospheric CO2 levels. And I'm going to just show you 2 slides on that without going through all the arguments. This was from a paper that was published in 1995 by Rob Rye, Phil Kuo, and Dick Holland at Harvard, Dick Holland, you all are not geochemists, but so you may not know him, but he's a very famous geochemist who's done a lot of work on the rise of oxygen, among other things. And what they did in this paper is they looked at paleosols. Paleosols are ancient soils. Soils usually don't get preserved because they get eroded away and washed into the ocean, but sometimes you cap them off with a volcanic flow and they get preserved. And then they looked for minerals in these ancient soils. In particular, they looked for the mineral siderite, which is iron carbonate. And then, the iron carbonate would form by reactions with gases from the atmosphere. CO2 goes into the carbonate, and they went through geochemical arguments, and they used that to try to place an upper limit on they didn't see siderite in these paleosols, and so they said CO2 had to be below a certain limit in order to constrain, not to form the siderite. So this is now, this curve B, this is a figure from their paper. That is the upper limit on CO2 from the paleosols, according to them. This is log PCO2 in bars. So we're at 3 × 10 to the minus 4 bars. 2 is down where that red arrow is, off graph, off scale. And that's the upper limit from the paleosols. This curve A, that's the limit from climate models. That's the one that I just showed you at 2.4 billion years. And these things are functions of temperature because the chemical reactions that form siderite are temperature dependent, and the climate model, the surface temperature, depends on the CO2 level. And so the bottom line of this is that if you believe their argument on the paleosols, then there wasn't enough CO2 in the atmosphere to actually warm the climate up, and you would need other greenhouse gases, like, for example, methane. And they actually suggested that in their paper. Now, since that time, there have been several other geochemists who've gotten into the act, trying to use other types of evidence to place constraints on CO2. There was a paper that came out by Minnick Rosing and colleagues in Nature last spring, including Norm Sleep is a co-author on this paper, and we've been arguing about this ever since.
I know this paper.
Yeah, so this paper is very controversial. There's a big discussion going on right now. I wrote the news and views on this thing, and so this is a figure that's modified from my News and Views article. And the way this is graphed here is this is CO2 partial pressure in bars on the vertical scale, time before present in billions of years, and solar luminosity down here, increasing to the right. Now these two solid curves, those are some new climate calculations by Philippe von Paris, who works with Heike Rauer over in Germany. So there are some other groups that are now doing these climate calculations. And they've placed limits. They did it between 0 and 15 degrees Celsius, but it's very similar to the older calculations that I published. Let's see, here's the Rye et al. Limit that I just showed you, the upper limit. That one works with the climate models because it would actually be within the range, according to them, although it's a little on the cold side. There's some more estimates from paleosols from Nathan Sheldon at Michigan. Here's this new estimate from the Rosing et al. Paper. They're using banded iron formations, which I won't talk about this time, but I will talk about next time. These are iron formations that form in the ocean. And the interesting thing about it is they get, if you believe their analysis, they get an upper limit on CO2 that is only 3 times today, because today is right here, and their upper limit is 1,000th of a bar of CO2, or 3 PAL. Well, that is way below the amount that you need to warm up the climate. And so you either need lots of other greenhouse gases, or in their paper, they suggest that it's an albedo feedback. So remember that the climate depends on the greenhouse effect, but also on the albedo. And their argument in that paper is that, I've told you that clouds are the most important part of the Earth's albedo. Clouds need cloud condensation nuclei in order for them to form. And a lot of those condensation nuclei come from sulfate particles in the atmosphere. Where does the sulfate come in the marine boundary layer? Well, it's coming from the oxidation of biogenic sulfur gases like dimethyl sulfide that's being given off by eukaryotic algae. And the eukaryotic algae were not there back in the Archean, so you didn't have the sulfur gases going in, and so their argument is that you formed clouds, but the particles were bigger, not as finely divided as they are, and so they sink out of the atmosphere quicker, and you don't get the albedo that you get today. You get sparser clouds that rain out more easily. So it's kind of a complicated thing. Could be right, although my colleague Kevin Goldblatt has redone these climate calculations. He thinks they're optimistic on the amount of warming you could get out of that. So I think I'll quit with that. There's a big debate going. There's some comments on the Rosing et al. Paper that have been sort of kicking around at Nature for the last 9 months or so, and they're about to come out. And there's going to be a big discussion on this at the Goldschmidt conference this summer, which is a conference of geochemists. So maybe we'll decide who's right on the Rosing paper. Now, you go back to Sagan and Mullen. Sagan and Mullen didn't try to solve the problem with CO2. They also liked other greenhouse gases. And in particular, they really liked ammonia. They mentioned both ammonia and methane, but they liked ammonia the best. The reason is that ammonia is a really good greenhouse gas. It's like water vapor. It absorbs over nearly the entire thermal infrared spectrum. So if you could get somewhere between 10 and 100 parts per million of ammonia in the atmosphere, then you could solve the faint young sun problem all by, just with that gas. And why did they suggest methane and ammonia? Well, these are reduced gases that react with oxygen, and so they're not that abundant today. But at the time Sagan and Mullen did their work, Preston Cloud, who was a geologist at UC Santa Barbara, had already published his work on the rise of oxygen. And so we were pretty sure by that time that oxygen was low back in the Archean. So this is where it gets mixed up with the oxygen story, and I'll show you one slide on oxygen. This is not from Preston Cloud's work, but it's from Dick Holland, whose name I've already mentioned. Dick sort of picked up where Preston Cloud left off. And what he's graphed here is a bunch of different geochemical indicators of oxygen, which I'll talk more about tomorrow. This goes in time from 3 billion years up to, before present, up to 0.6 billion years. There are blue boxes on the left, which represent low oxygen, and there are red boxes on the right, which represent high oxygen. So the change between these, according to this graph, is at about 2.2 billion years. There's some new age dates on this. We think that you should really push that back to about 2.4 billion years. And without belaboring this, let me mention two of these things, because I'm going to come back to them at the end of this talk. Red beds, that's oxidized iron in soil. These come in, that's evidence of high oxygen. And detrital uranium minerals, reduced detrital minerals are ones that don't dissolve during weathering. And so detrital uranium ores, that's the mineral uraninite, are evidence of low oxygen. I'll explain more about that next time, but I just want you to remember. And by the way, these are the banded iron formations down here at the bottom. This is what Rosing et al. Are using. Those are a little different. They actually last until about 1.8 billion years ago. We think that they mean that the deep ocean was anoxic and filled with soluble ferrous iron up until that point. Okay, and then there's other stuff from sulfur isotopes, which I'll talk about next time. So the problem with Sagan and Mullen's idea was that, ammonia is a good greenhouse gas, but they hadn't considered its photochemistry. And, not too long after they published their paper, some former teachers of mine from University of Michigan, where I got my PhD, they were photochemists. And so they pointed out that ammonia is photochemically unstable. And the sequence goes like this. You photolize ammonia, knock off a hydrogen and make NH2. Then two NH2s makes an N2H4. That's the molecule hydrazine, which is actually used as a propellant in rockets. So it's familiar. It's used in the little booster rockets that are used for attitude adjustment because it reacts with oxygen. But then the hydrazine reacts with hydrogen, and it gets photolized. and two N2H3s goes to this unstable molecule, and it ends up coming apart into N2 and H2. And of course, N2 is N triple bond N. The hydrogen escapes to space, which I'll talk about also later in my lectures. It's really hard to reform the ammonia in the atmosphere, so that, if you put in the photochemistry, it's hard to keep the ammonia around unless you have a really huge source, and nobody's identified a really big source of ammonia for the early atmosphere. So the ammonia doesn't really work as well as advertised. All right, but Sagan and Mullen also mentioned methane, and methane is a much better idea because methane also photolyzes, but it only photolyzes below about 145 nanometers, whereas ammonia photolyzes out to 230 nanometers. Of course, there's many fewer solar photons at the short wavelengths, so methane is much more stable against photolysis than ammonia is. Why else should one like methane? And here I'm going to start to overlap with John for the next few slides. Methane is produced, almost all the methane, but not all of it. Most of the methane on the modern Earth is produced by methanogens, these organisms that John has talked a little bit about. And methanogens can make methane by a variety of different pathways, but one that is, I think, universally shared, but
one pathway, but they use different sources of carbon.
Different sources of carbons. So
one pathway.
One pathway. Many or all methanogens can use CO2 and hydrogen. All can. And so they make methane and water out of that. And they do this, they make a living out of that because that's downhill thermodynamically. So these methanogens are living, this is chemosynthesis. You're using the chemical energy of the available free energy, in this case CO2 and hydrogen, to drive your metabolism. At low temperatures, methane is thermodynamically favored. So now I'll pretend to be a biologist for 2 slides here. We think that the methanogens are ancient, and John may have already said this. For one thing, they should have been around because we think there were CO2 and hydrogen in the early atmosphere. So if evolution was clever, these organisms should have evolved early. But you can also tell this by looking at their DNA, and actually this fits in nicely with John's talk this morning because he showed you what we sometimes call the universal tree, where you're looking at the RNA in ribosomes. And I want to just mention the biology again because I know it's tough for many of you who are mostly physicists to get the biology. Ribosomes are the parts of your cells that are making the proteins, and these ribosomes are filled with RNA, which was a great surprise, I think, at first when it was discovered. At least it was a surprise to me to find that out. But in retrospect, it's not a surprise. This is a picture of what an ribosomal RNA molecule looks like. The RNA in the ribosome, RNA is single-stranded, whereas DNA is double-stranded. So DNA forms these sort of linear chains. RNA is like a protein. It can fold up. Because it's only a single strand, it folds up into loops. And then these loops have catalytic properties, just like proteins. Proteins fold into loops as well, and that gives you the catalysts of enzymes that are used in most modern organisms. But these, in the RNA, in the ribosomes, the RNA folds up into these complicated structures, and it catalyzes the formation of proteins. And that was one of, I think, the great discoveries of molecular biology in the last 2 decades. It won several Nobel Prizes for showing that that's the case. So this has led to this concept of the RNA world, that RNA preceded DNA and proteins, and there may have been some stage where organisms were mostly RNA, although they probably figured out how to make proteins at some fairly early point. Anyway, that's what you're looking at when, these days the biologists sequence DNA, but they're looking at that section of the DNA that codes for ribosomal RNA. And that's where they get this tree that John's already put up earlier this morning. This is an old version of the tree that I got from Norm Pace about 10 or 12 years ago, so it may not be totally up to date. But, you know, it's got the 3 domains of life, the archaea, the bacteria, and the eukarya. The methanogens are right here. They're on one branch of the archaea, and the root is probably somewhere down here. There's some argument as to where that root should be, but the argument here, distance from the root is in some way related to evolutionary time, although it's probably not a linear relationship. And this is additional evidence that the methanogens are ancient. Now, just the reason I like to keep using this old tree is if you look here at the tip of the eukarya, there's Homo, that would be us, right? That's Homo sapiens. And then there's Zea and Coprinus right by it. And who knows what Zea is? I'm sorry? It's corn. Yeah, and Coprinus is mushrooms, right? So on this tree, we plot right between corn and mushrooms. And, you know, why is that? Well, it's because this part of the DNA has to change very slowly, because this is where your proteins are made in the ribosomes. And normally, if you have a mutation in there, you destroy your protein manufacturing machinery, and it's fatal. So not many mutations survive. And it does mutate, you know, and this ribosome changes over time, but very slowly. And so when you look, that's why this particular molecule is so useful. When you look at this molecule, you're peering way back into evolutionary time. As opposed to looking at other sections of the DNA. DNA is used in forensic analysis when you're trying to solve a crime scene, because you can tell differences between humans by looking at other parts of the DNA. But those things change very rapidly, so you would never be able to look back far into time. And also, all organisms have ribosomes, because we all have to have proteins these days. So this is something that can be universally used. All right, so I'll quit being a biologist, and that's probably as far as I'll forage into biology. Now, I mentioned that I've been harped on feedbacks in the last talk. There are also feedbacks in the methane cycle, and there's 2 of them that I'll talk about. One has to do with temperatures at which these methanogens grow. It turns out that methanogens can grow at a whole variety of temperatures, but the ones that live at high temperatures can reproduce and grow faster than the ones that live at low temperatures. So actually, thermophiles, methanogens that live at reasonably high temperatures, will outcompete mesophiles as the temperature gets warmer. Mesophiles live at more moderate temperatures. And so there's a positive feedback loop, which we can draw like this. If you increase the surface temperature, you should make conditions more favorable for the thermophilic methanogens that can grow faster. They should produce more methane. That gives you a bigger greenhouse effect, which increases the surface temperature. So you go around that loop. There's no negative couplings. That's a positive feedback loop in the methane cycle. Furthermore, if you get a lot of methane in the atmosphere, there's photochemistry that goes on with the methane. It doesn't just sit there. And so at low methane concentrations, it tends to oxidize, even if there's not oxygen around. But at higher concentrations, it polymerizes. And I won't show you a lot of photochemical calculations, although I'll come back to this when we do prebiotic oxygen. If you run a photochemical model of a methane-rich atmosphere, you find out that you make lots of other hydrocarbons from photolysis of the methane. That includes ethane, which is C2H6, and ethylene, C2H4, and acetylene. The way you make these, there's different pathways, but you can photolyze methane directly and knock off a hydrogen, or you can photolyze water and make the OH radical, and then the OH reacts with methane and gives you CH3 methyl radicals, and then these methyl radicals react with a third body and give you ethane. And so that pathway leads to ethane, which is C2H6.
Jim?
Yes?
Just make a really short comment and give you guys a little bit of homework. because you talked about the rapid growth of something like a methanogen. Some of the methanogens have a doubling time of between 15 and 20 minutes, so they double. So I write that down. The mass of a single cell is 10 to the minus 13 grams. Now, if it divides every 15 or 20 minutes, and it does that for 2 weeks, what would the overall biomass be? So go on.
Okay, I'm glad you interrupted because I'm looking at my watch. I got 5 minutes. I'll show you one more slide and then we'll truncate this and I'll come back to it. So you can make ethane, and ethane's a greenhouse gas actually. It has a couple of absorption bands that matter. One of them is right there between 11 and 12.5 microns, which remember I mentioned the 8 to 12 micron window region. So methane is one, or ethane is one of these gases that you put it in there. It's very effective because it basically stops up that hole. And, you know, the infrared radiation is leaking out to space through that 8 to 12 micron window. And if you put gases in there that can fill up that hole, then you get a lot of greenhouse effect out of them. So I know that there are people that want to ski. I'll quit now. We got 4 minutes to go until 11:30, so maybe I'll take a couple of questions and then I'll finish this up next time so that I don't have to rush through it. Thank you. Yes, Elaine.
What's before the origin of life? Because we need water right at the beginning, before methanogens.
Yeah, so before the origin of life, there would be some methane. It comes from processes like serpentinization. So there are abiotic ways of making methane, but they don't make as much as the methanogens do. And you know, I was just discussing this with John earlier. You know, when they look at the mid-ocean ridge vents, these hydrothermal vents, one of their toughest problems is to figure out there's methane coming out, and they're trying to figure out whether it's biotic or abiotic. And you can do that with the carbon isotopes, right?
Does it work? Does it work to warm the Earth?
You know, from what we know, then there wouldn't be enough methane around prebiotically to get much greenhouse effect. So presumably CO2 would compensate through the carbonate silicate cycle. But then once methanogens come in and start producing methane, and then you get ethane from the methane, then that would warm temperatures up, and that would increase silicate weathering, so CO2 would come down. And then I'll show you it gets more complicated because there's a negative feedback that comes in there. If you get too much methane compared to CO2, then you start to polymerize the methane and you get haze and it causes cooling. But I'll save those slides for the next time. Yes?
You had an earlier fainter sun, but you also have a more active sun, higher X-ray flux with a lot of energetic particles.
That's right. So in the visible, the sun is getting more luminous with time, but it was spinning faster early on, and there was more magnetic activity. So there's a lot more UV and FUV and X-ray radiation coming off of it. And that doesn't affect climate directly, but it impinges on hydrogen escape because it affects the temperatures of upper atmospheres. And so I'll talk some about that when I talk about hydrogen escape. That's also, though, how Brian Wood and colleagues, that it's not just the high energy photons coming off the sun, but you also get enhanced stellar wind, and so that's how you're actually losing significant mass for a little while during that process.